Hello, in this video I'm going to explain a light and optics math concept referred to as Snell's law. So first off, our content and language objectives. The content objective is I can solve Snell's law math problems. Language objective is I can write an explanation of why you sometimes can't see objects above the surface when you're in the water in a pool. So what is Snell's law? Snell's law has to do with refraction. There are many things that can happen when light runs into an object. It can bounce off of something, it can reflect, it can be transmitted or just pass through an object, it can be absorbed. But what we're talking about here is refraction, is when light bends. And so what we're going to talk about with Snell's law is how you can predict the angle that light is going to bend when it encounters a new substance. Just a few Snell's laws variables that we're going to talk about. First, we just mentioned refraction is when light bends as it passes from one material to another. There is a term that's called a normal. And so if you have two different surfaces shown in here in white, called N1, and we'll talk about that term in a minute, and then blue over here, the normal is a 90-degree angle to those two surfaces. It's perpendicular to those two surfaces. An angle of incidence is like the incoming angle to that substance. An angle of refraction is the outgoing angle as light bends, I guess, as it passes to a new substance. And an index of refraction, we're going to talk about these terms N1 and N2. Light travels different speeds through different objects. When an N value is 1, that's when light travels its normal speed, 3.0 times 10 to the 8th meters per second. If the index of refraction was 2, that would mean light travels half that fast. That's kind of what you're dividing the speed of light from as it travels through a different substance. Snell's law equation that you can see on this slide, N1 times sine theta is equal to N2 times sine theta 2. And so we'll go through and we'll explain that and look at a sample problem in just a moment. An example problem involving Snell's law, it says if light in vacuum approaches a diamond at an angle of 43 degrees with respect to the normal, what angle would it refract at? And so light's going to travel different speeds through different substances. In a vacuum, light travels its normal 3.0 times 10 to the 8th meters per second. But in a diamond, if you look at the chart that's found in the bottom right of this slide, the index of refraction is 2.41. There are no units, it's just a number here. And so that's why diamonds are so sparkly, is light bends quite a bit. And so you get lots of bouncing around of light in a diamond. And so to solve this problem, you'd use the equation again for Snell's law, N1 times sine theta 1. So the index of refraction of substance 1 times the angle as it's passing through substance 1 is equal to N2, the, again, index of refraction of substance 2 times sine theta 2. N1, what that is basically the speed of light in a vacuum. And so it says that the index of refraction in the table to the bottom right for a vacuum is 1.00 exactly. Light travels fastest when it's not bumping into different things. So when there's a vacuum, there are no particles it's running into. You never need to memorize these indices of refraction shown in this chart. You just need to look them up. Google them if you need to. The second thing that we're given here is the angle as light approaches a new substance, 43 degrees. We are given that it approaches a diamond. And so again, you can look at the table in the bottom right-hand corner, and it says the index of refraction of a diamond is 2.41. And so the only thing we don't know is angle 2. And so that's what we're solving for is angle 2 here. To solve this problem, again, I've just identified in this slide, paused if you need to, all the different information that you're given in this problem, just to show you kind of what it is, where it was in the problem, and how I plugged it into this equation. And so when I try to solve this, the first thing I'm going to take care of is I'm going to type in a calculator 1 times sine 43. Make sure your calculator's in degrees, and I come up with 0.68 is equal to 2.41 times sine theta 2. Next thing I'm going to do is divide each side of the equation by 2.41 to eliminate that on the right side of the equation. So 0.28 is equal to sine theta 2. And then I'm going to hit that sine to the -1 button on my calculator to give me my angle of refraction, which is 16.44 degrees. Again, it's important to hit that DEG button or that D button that's on your calculator so you're in degrees and not radians. if you're dealing with degrees. Critical angle. So sometimes light does not bounce out of an object. What this image shows you is that sometimes light will refract, but sometimes if your angle is too shallow, what you'll have is internal reflection. And so when you cut a diamond, they're these ideal cuts, these cuts where you get the most reflection and refraction out of a diamond, so you get that sparkle. But if your angles are not quite right, you won't get light leaving the top of that diamond. You won't get just that beauty that you see in a diamond. And so what you can see sometimes if you're moving from a substance, again, where you have a high index of refraction to a low index refraction, like from inside the water to inside the air, you're moving from where light's moving pretty slowly in water to very fast in air. You can see in this picture what can happen with a critical angle, where you can see right above you out of the water into the space above it into the air. But if you look at those less steep angles that you can see off in the distance, off to the right, off to the left, and then far out, you get that total internal reflection. And that's why you can't see out of a pool if you look at certain angles, is because you've exceeded this critical angle. So if you're ever trying to solve a problem involving Snell's law and you get an error on your calculator, you're either in radians, which is a possibility, or you've exceeded this critical angle and light will not refract out of this substance. That's the end of this video overviewing Snell's law, a light and optics topic involving math. If you have any questions, please feel free to stop by during homework help hours or period 1A. Have a great day. Thank you.